This is your third lecture of analog communication. Till now, what we have seen concept of your communication system. It includes your block of communication system, and it includes your concept of analog communication and digital communication, analog signal and digital signal. Later, what we have seen the concept of modulation, and it includes your amplitude modulation, frequency modulation, and your phase modulation. So in this lecture, we will see some very important equation related to your frequency modulation and your phase modulation. So let's start the lecture. So till now, what we have seen for angle modulation, basically there are two types of angle modulation. First one is your frequency modulation and second one is your phase modulation. For frequency modulation, there will be change in frequency in your carrier signal, and rest of the parameter will remain same. For phase modulation, there will be change in your phase of carrier signal with respect to instantaneous change in your masses signal, and rest of the parameter will remain same. So what we have seen basically there are two types of masses signal, two types of signal. The first one is your masses signal and second one is your carrier signal. For carrier signal, we can write like this equation, because for signal, basically we are having three parameters: amplitude, phase, and frequency. So we can relate phase and frequency by using this equation. Your phase is nothing but it is your product of frequency and time. So we are having two equation that is very important. That is frequency is nothing but it is your derivative form of your phase. Second one is what? Your phase is nothing but it is integrated form of your frequency. So we need to remember these two equations for the derivation of your frequency modulated wave and your phase modulated wave equation. So this is your FM versus PM equation. In this slide, we will derive your frequency modulated wave equation and phase modulated wave equation. Okay, so in this slide, basically all the equations are very important, including its derivation concepts also. Okay, so in the starting, first we'll see this FM and then we'll see this PM. So as we know, this FM and PM are very closely related. So that's why we are doing its comparative study, right? Because it is advisable to do comparative study when two things are very closely related. Okay. So for FM and for PM, we are assuming that this AC cos theta I, this AC cos theta I is your modulated wave equation. Okay, as you know, for FM, we need to vary carrier signal frequency with respect to message signal, right? As you know, for PM, we need to modulate, or we need to change carrier signal phase with respect to message signal. Okay. So in the case of frequency modulation, what we are doing? We are changing carrier frequency with respect to message signal by some constant. Here kf is nothing but it is your frequency sensitive constant. In the case of PM, what we are doing to get your instantaneous theta, we are modulating carrier phase by some amount of your, by according to your message signal, by some phase sensitive constant. Kp is nothing but it is a constant which is phase sensitive. Okay, so in the case of FM, we are having Wi. In the case of PM, we are having theta I, right? So what is your KPAM? This KPAM term is nothing but it will be some constant because both are constant term. So in the case of PM, we are calling this KPAM as a peak phase deviation, and we are denoting it by beta PM. We are calling it modulation index also in the case of phase modulation. But in the case of phase frequency modulation, this KFAM, this constant term, this constant term, this constant term, we are calling it peak frequency deviation and denoted by delta omega, right? Not beta, right? So in the case of FM, we are calling KFAM as a delta omega. In the case of PM, we are calling KPAM as a beta PM, that is peak phase deviation, and in the case of FM, it is your peak frequency deviation. So in the case of FM, you can see what is your equation actually. Your equation of frequency modulated wave is AC cos theta I. So we need to have this theta I term. So to get this theta I term, what we need to do? We need to integrate. We need to integrate this term. We need to integrate this instantaneous frequency to get instantaneous theta. So we have the integration process has been done, and we'll get this equation for theta I. So what we have seen, when you are getting this term theta I, there is one term you can notice here, that is delta omega by omega m will come as a part of sine omega t. This term is nothing but this is your modulation index in the case of your frequency modulation. Okay, now we need to put this theta I value in your final AC cos theta I equation, and similarly in the case of PM also we need to put this theta I in your eventual equation that we have assumed earlier, that we have assumed previous. Okay, so what you will get? You will get this type of equation. When you will put this value of theta I in the both case of FM and PM, you will get this type of equation, right? So in this case of PM, what you have done? You have your simple empty actually. But in the case of FM, what you have done? You have integrated. You have integrated your WI. Basically, when you have integrated this WI, what basically you have integrated? You have integrated this term. And this term is what? This term is your message signal. So indirectly, you will get this equation for your FM because you are integrating message signal. And in the case of PM, you will get direct empty because you don't need to integrate or differentiate in the case of PM. So this is two equation for your FM, and here we are having two equation for your PM, and these four equations are very important to understand the frequency modulation and your phase modulation. So your next slide is relation between your FM and PM. What is it? You are having in first take your case of PM. You are having two boxes. First one box is for derivation, and second one box is for FM that contains this equation. What you will do? You will pass this empty through first equation, first block. What you will get? Derivative of your message signal, and then this derivative of your message signal, you will pass this equation through your FM, this block, this second block, and what you will get? You will get your PM signal. Just point out one thing. When this derivative form of your message signal will pass through this FM block, means what? We are just replacing this empty with your derivative form of your message signal. And when you are putting derivative form of your message signal in place of your empty, what you will get? Your integration and your derivative will cancel out each other, and it will give you PM signal. Similarly, in the case of FM, we are having two blocks. First one block is for integration, and second one block is for PM, that is phase modulation. So first you will integrate your message signal, and then you will pass that integrated form of message signal through your second block, and that block contain this equation. So basically what you are doing, you are replacing this empty with your integrated form of message signal. So what you will get? You will get this equation, and this equation is what? This equation is your FM signal. So this is basic relation between your FM and PM. How you will get PM signal from your FM signal, and how you will get PM signal from your FM signal from your PM signal. This is basic difference. This slide explains the basic difference between your FM and PM. So what is the basic difference? As we know, empty is what? This is the equation for your empty, and CT is what? This is your equation for CT. Same for PM also. So in the previous slide, we have seen we need to modulate frequency. In the case of frequency modulation, so this is your instantaneous frequency. And in the case of phase modulation, we need to modulate the phase. So this is your instantaneous phase equation. So in the case of phase modulation, this KPM AM is what? This is your peak phase deviation. And in the case of FM, your KF AM is what? This is your peak frequency deviation. Okay. So here you have seen this. This is your KP beta PM, and this is your peak phase frequency. Now we need to have peak frequency deviation in the case of PM also. So what we will do? We will differentiate this term. We will differentiate this term, and when we will differentiate this term, this omega m will come here, right? And what we will get? Peak frequency deviation. We will get this kind of equation for your peak frequency deviation in the case of PM. Now notice one thing. In the case of FM, your peak frequency deviation is independent of your omega m, that is message frequency. But in the case of phase modulation, your peak frequency deviation is dependent on your message frequency, right? So this is basic difference between your FM and PM. Your frequency deviation is independent of message frequency in the case of FM, and in the case of PM, your frequency deviation is dependent of your message frequency. So this is the basic difference between your FM and your PM. So this is what we have seen, some explanation, some important explanation of the important equations related to your FM and your PM.